We are starting from the sixth one because the other ones before it are about equivalence relation. Okay. So what do we have in this one? Here a relation has been defined on the plane. On the plane means of course this set, which is your usual Cartesian product of two copies of the set of real numbers. And the relation relates to ordered pairs of real numbers if either y0 minus x0 square is less than y1 minus x1 square, or if these two real numbers are equal and x0 is less than x1. If either of these two conditions is true, then we say that x0 comma y0 is related to x1 comma y1 by this relation. Or you can also express it more casually by saying that x0 comma y0 is less than x1 comma y1. Now we have to prove that this is a legitimate ordered relation on the plane, and we have to describe it geometrically as well. Now before we start the solution, let's observe one thing. Do you remember that in this book we have decided to denote the ordered pair whose first component is A and second component is B by this notation and not the usual ordered pair notation? Here, however, the author is not following that convention. I don't know why. But anyway, let's just go with this old notation and start solving the problem. Okay, so what do we need to show here? We need to show that this relation satisfies comparability, non-reflexivity and transitivity. Let us also recall briefly what these things are. Say you have a binary relation, something, say let me just use this symbol itself, on a set A, which relates two elements of A. When do we say that this relation satisfies comparability? It is when you take two elements in A which are distinct, then either x is related to y or y is related to x. When this is true for this relation, we say that it is comparable or it satisfies comparability. What is non-reflexivity? Non-reflexivity tells us that the relation should not relate any element to itself. No element of A is related to itself by the relation. And transitivity of course has its usual meaning. If x, y and z are three elements in A, not necessarily distinct of course, such that x is related to y and y is related to z, then x is related to z. We have to show all these three things for our relation. Okay, so now we can start the solution. Let's just take 3 points first. x0, y0, x1, y1 and x2, y2 in R2 in the plane. Let us first show that the relation is it satisfies comparability. Assume that this is not equal to this. That means these two ordered pairs are distinct. Now we have to prove that either this is less than this or this is less than this. If now, according to the definition of this relation, we have to look at these two real numbers, y0 minus x0 square and y1 minus x1 square. Three possibilities are there. If y0 minus x0 square is less than y1 minus x1 square, then this is less than this by the definition. However, the opposite can also happen. If y1 minus x1 square is less than y0 minus x0 square, then again by the definition, this time x1 comma y1 is less than x0 comma y1. But there is a third possibility also where these two are equal. What about that one? Now, let them be equal. If these are equal, then which one is greater and which one is smaller, that will be decided by the first components of this ordered pairs, again by our definition of relation. That means if x0 is less than x1, then we will say with this condition, of course, then we will say that this is less than this. And if x1 is less than x0, then we will say that this is less than this. But if they are equal, is that a possibility? Is that a real possibility that x0 is equal to x1? Note that if x0 is equal to x1, then x0 square is equal to x1 square, and so y0 will also be equal to y1. Why? Because these two are equal. If x0 and x1 are equal, then cancelling that thing from both sides, you get y0 equal to y1. But then x0 comma y0 is equal to x1 comma y1. Contrary to our choice that they are not equal, or contrary to our assumption. So, they cannot be equal. Now, they cannot be equal and they are real numbers, so one of them will be less than the other. If x0 is less than x1, then combined with this equality, what does the definition tell us? The definition then tells us that this is less than this. Whereas if x1 is less than x0, then x1 comma y1 is less than x naught comma y naught. So we see that no matter what the situation is, either this is true or this is true. In other words, these two distinct ordered pairs are comparable. That means we have verified the fact that this relation satisfies comparability. Now next we go for non-reflexivity. That means we now have to prove that we cannot have x naught comma x naught less than itself, but forcefully suppose that that is true. Next, suppose that this is really less than this, then by the definition either y naught minus x naught square is less than y naught minus x naught square, or this is equal to y naught minus x naught square and x naught is less than x naught. But you can clearly see that none of these two conditions can be true. A real number cannot be less than itself. Again, this real number cannot be less than itself. Since this is not possible, our supposition is false. That means we must have this not less than itself, and that is our non-reflexivity. And finally, we go for transitivity. Next, let this be less than x1 y1 and x1 y1 be less than x2 y2. Alright, so now we are going to use the definition and write what their meanings are. Thus, either from this relation we get y naught minus x naught square less than y1 minus x1 square, or they are equal and x naught is less than x1. But a similar thing will be obtained from the second one also. Also, either y1 minus x1 square is less than y2 minus x2 square, or they are equal and y1, sorry, not y1, x1 is less than x2. Now depending on which ones you choose from both of these things, there are 4 cases. I think it will be a good idea to tackle the cases separately by actually writing headings. Case 1. In case 1, what happens is that this is true. I mean, there is this is an OR statement, right? It's a disjunction. In case 1, this is true, and from here, this is true. Suppose y0 minus x0 square is less than y1 minus x1 square and y1 minus x1 square is less than y2 minus x2 square. Then you can clearly see, I mean, this less than is our ordinary ordered relation we have on the set of real numbers. And we know that that relation is transitive. Then, so from that transitivity, we get this. So, by the definition of our relation, x0 comma y0 is less than x2 comma y2, and in fact this is what we wanted. So in case 1 we have our thing. Next comes case 2. In case 2 we have this, but from this second one we have this. Suppose that means here we have this inequality y0 minus x0 square is less than y1 minus x1 square and y1 minus x1 square is equal to y2 minus x2 square and x1 is less than x2. Then you can clearly see that you can just write this in place of this, and that itself will again give you this inequality. That is, you will get this pretty directly. So again, this is less than x2 comma y2. So again we are getting what we want. Next, case 3. In case 3, from the first one we take the second option, and from the second one we take the first option. That is, this time y0 minus x0, I needed to write suppose this is equal to y1 minus x1 square and x0 is less than x1. So this comes from the first option, the first inequality, and from the second inequality we take the second option, that is y1 minus x1 square is less than y2 minus x2 square. This time here you can write y0 minus x0 square, somewhat like this one. So that will give you y0 minus x0 square less than y2 minus x2 square. Hence, again you are getting your desired inequality. And finally, there is case 4. In case 4, you take the second option from both the things. That means this time this is equal to y1 minus x1 square and x0 is less than x1 and y1 minus x1 square is equal to y2 minus x2 square and x1 is less than x2. Alright, so for these quantities now we just have equality. This is equal to this, which is equal to this. So we can first write that y0 minus x0 square is equal to y2 minus x2 square, but at the same time x0 is less than x1 and x1 is less than x2. So obviously x0 is less than x2. So again, by the definition of our relation, here also this becomes less than this. So that means in all the cases we are in fact getting this inequality, and that is why our relation is transitive as well. So we have shown that it satisfies comparability, it is non-reflexive and it is transitive, and that is why it's the legitimate ordered relation. So this is an ordered relation on the plane R. Okay. Now next we go for what all these things mean geometrically, because the plane, we are calling it the plane. Truly speaking, the relation really has nothing to do with geometry. If you just simply consider its definition and you have verified everything without using geometry. But there is an obvious geometric connection, because this set is not simply a set of some objects. There is a way of relating the elements of this set to geometric points in your 2D plane, which is our usual, we get the x and y axis that way through that association. So if you use that association now, how do all these things look geometrically? That's the question. So let's see that part next. But before we do that, we are going to need some notations. For any real number C, let what name shall I give the sets that I am thinking of? one set will be, you can see that I have drawn a parabola here. Why a parabola? It will become clear. I want to call the set of points that lies above the parabola, all the points that lie above the parabola, say UC, up and or upper, and the ones that lie below, lower. Okay, so let me just call this UC. UC is the set of all points in the plane that's understood such that y minus x square is greater than c, and LC as the set of all points in the plane such that this is less than c. Alright. Now let us take any element in R2. Say this point x0, y0. Now consider any point in R2. Alright. Let C0 be y0 minus x0 square. Then our point lies on the parabola y equal to x square plus c naught, or y minus x square equal to c naught, same thing. You may notice that this parabola is just a vertical shift of your familiar parabola, which is y equal to x square. Depending on what c naught is, either this will go up or down. The axis of this parabola will continue to be the y-axis. Okay, however, because it can go up and down depending on the value of c naught, so its focus will lie wherever it lies. Okay, so in general it's going to look like this. I have drawn a general situation. It can also, the vertex of the parabola may lie above the x-axis or it may lie below the x-axis depending on what c naught is. If c naught is 0, then the vertex will coincide with the origin, so the parabola will pass through the origin. That is your familiar y equal to x square. Alright, fine. Now, what are these sets here? If this is our c naught, then this is your UC naught. UC naught consists of all points that lie within this cup, but not on the parabola. On the parabola, there are those points x comma y for which y minus x square will be equal to c. The ones for which this is greater than c, they lie here in that region, open region. Whereas the ones for which this is less than c, they lie in a sense you can say they lie outside the parabola's region, which I cannot say it bounds because it does not bound, but you get my point. Okay. Now, what does our order relation say? Our order relation tells us that, say, you have any point x comma y on the plane, then this is less than x naught comma y naught if either y minus x square is less than y naught minus x naught square, which according to our notation is c naught. Okay, so if x comma y is a point for which y minus x square is less than c naught, then x comma y will be less than x naught comma y naught. Now you can see that that is the case with all points which lie, for example this one, outside the parabola in this region L C naught. This means that any point on the plane which lies in the region L C naught is less than x naught comma y naught. Again I am repeating, L C naught does not have any point that lies on the parabola but outside, okay, below, outside, like that. So let's start this part of the solution by writing this. Oh, and because okay, since I am showing this, what about this inequality? This will happen when c naught is, that means y naught minus x naught square is less than y minus x square. This condition is satisfied by the points that lie in UC naught. So all the points that lie within the cap of the parabola are greater than x naught comma y naught. And again look carefully, we haven't said so far anything about the points that lie on the parabola. What about them? Which one of them are less than this and which one of them are greater than this? Any point, say you consider this point, say x prime comma y prime. For any such point, what is going to be what will be y prime minus x prime square, because x prime comma y prime has to lie on the parabola, so its coordinates must satisfy this equation. That means this will be c naught. However, that is equal to y naught minus x naught square. So in our definition of this relation, now it is time for us to think of the second part of the definition, because for this point and this point, these quantities are equal. Now which one is going to be greater than which one, that will be decided by the x coordinates. If x prime is less than x naught, then this point is less than this. But if x prime is greater than x naught, then this point is greater than this. Which means that for the points on the parabola, the ones which lie on this side are all less than this, and the ones that lie to the right of this point on the parabola again are greater than this. Now we have to write all these things. Okay, so the figure is in front of us, so it will be easy to write. Any point in LC naught is less than, but be careful of writing less than. You cannot just simply write less than, because this is not ordinary order relation, this is something special, and the objects that this relation relates are not numbers, but they are ordered pairs. So we put this within quotes. Less than in that sense is, oh, we have already, okay, is less than, we have already written this. Okay, so we have said whatever we had to say about the points in LC. Next, this is less than any point in UC0 for any point, okay, let me write in words, that way it will look nice. On the parabola it's less than this if it lies to the left of the chosen point. Also, x0, y0 is less than any point on the parabola that lies to its right. That's the thing. So one type of behavior for points which lie in this region, and also for points that lie within, and another type of behavior for points that lie on the parabola. It's like it's as if the parabola is a twisted version of the x-axis. Just like on the x-axis the points increase to the right, here also the points increase in this direction. So this is the geometric description of this order relation. Let's see another one, the next one. In a very vague sense, this relationship is somewhat like the dictionary order, but a twisted dictionary order. 7. Show that no, it won't be the restriction, a restriction of an ordered relation is also an ordered relation. What do we mean by restriction? Let's see. Let A be a, say, I think I need a bit of ink. So we will start by considering an ordered set A. Let A be a set with ordered relation less than, and let B be a subset of A. Okay. Because this less than is after all a binary relation, so you recall the definition of relation. Truly speaking, this less than is actually a subset of the Cartesian product A times A. That's what we mean by a binary relation. It's a special type of binary relation, it's an ordered relation, but basically that's what it is. It's a subset of A times A. Now, since B is a subset of A, so B times B is a subset of A times A, and that's why you can take the intersection of this subset and B times B. That will be a subset of A times A, of course, but in particular of B times B. That is the restriction. So, consider the restriction. Let us denote it by less than B of this relation on B, i.e. what that really means. This is the intersection of this relation and B times B. Okay, this looks very strange, but do not forget that this is a subset of A times A. Clearly, this is a subset of B times B. That means, by definition, this restriction is a legitimate binary relation on B. Okay. Next, we have to prove that it's an ordered relation, just like this is an ordered relation on A. So again, comparability, non-reflexivity and transitivity, we have to verify these things. So let's start by taking any three elements in what? In B. Let A, B and C be any three elements in B. Assume that A and B are not the same. Now, since A and B also lie in A, because B is after all a subset of A, we have, now I am no longer going to write A less than B. Instead, I will write ordered pair, because we are viewing this as what it really is. It's the set of ordered pairs. Either A comma B in this relation or B comma A in this relation. And this is just we are writing the fact that this relation is satisfying comparability. But we also have this fact that A comma B and B comma A both belong to B times B, because after all they are elements of B. So if this is the case, then A comma B will belong to both this relation as well as B times B. So it will belong to their intersection, which is this. On the other hand, if B comma A belongs to this, then B comma A also belongs to B times B. So it will belong to their intersection, which is this. So we write, hence, either this belongs to less than b, or b comma a belongs to less than b. So we have proved that this new relation, this restriction satisfies comparability. Next, suppose the next one is non-reflexivity. Suppose it is not non-reflexive. Suppose that a comma a belongs to this. That is, by this relation a is related to a. Then something should go wrong, but what? But then a comma a belongs to this relation as well. Why? Because this is, after all, the intersection of this and this. So it's a subset of both this relation and b times b. So this belongs to this, which is not possible. Why? Because if this is true, then the non-reflexivity of this ordered relation will be violated, which cannot be true. That is why. Thus, this cannot belong to this relation. That means our restriction also satisfies non-reflexivity. Finally, let a comma b and b comma c both belong to this. Then they also both belong to the relation on the set A, because this is a subset of this. But we already know that this is transitive. This implies, if you want, you can write the reasons. Instead of writing like this, you can write more. Since this is transitive, so we have this. I am not going to write all these things. Okay. This implies a comma c belongs to this. But we also have this in b times b. Hence, this belongs to the intersection of this and this. That means less than b. So, this is an ordered relation on B. Okay, so that's the restriction. In other words, if you have an ordered set and you restrict that ordered set, the ordered relation on the ordered set to any subset in this sense, then that subset itself becomes an ordered set, and you can call it an ordered subset. It's like the notion of a group having a subgroup. Restricting the binary operation of the group on the subset gives us a subgroup. That's not always the case, unlike this one, but it is similar. Okay, so let's just end our discussion here itself. There are other problems also after this that we will solve in the next topology video. And tomorrow, as usual, we have our trigonometry. We are nearing the end of trigonometry, and tomorrow we will solve. We have actually already completed miscellaneous examples. So tomorrow we will start solving miscellaneous exercises. So with that, I just wrap things up. So see you tomorrow with trigonometry. Until then, this is me, Lucifer, from A Mathematical. Have a nice night.